This is the final video of learning module 1, and this is where we close the loop with the data-driven decision-making process by providing an overview of the descriptive and inferential statistics that follow after your sample has been properly chosen. So you saw from the previous video that in a data-driven decision-making process, you start off with defining the problem, choose from the population if data is available. If not, you create your own data, and irrespective of whatever data you are choosing, be it from a subset, be it from creating a data, you have to ensure that it's generalizable as well as projectable, which is where randomization and representation is of importance. And once that sample is ready, now you start looking into organizing and summarizing data. This is where the descriptive statistics aspect comes in. So when it comes to descriptive procedures, there are two parts to the process. Okay, the first part is where the visualization of data happens. So this is where you are trying to understand the data as is. Understand that descriptive procedures do not help you infer. That's why descriptive statistics are different from inferential statistics. Descriptive procedures provide you what we define as a smell test. Okay, it just gives you a feel of how the data is. When you visualize a data set, you can kind of get a feel of how the data is behaving. Does that mean that you can conclude based off of that? No, because there is no confidence in your judgment unless you use statistical techniques. So if you look into this bar chart as an example, okay, so um, total copies sold by market class. So your x-axis is total copies sold, your y-axis is market classification, be it social sciences, be it businesses. Of course, it feels like business sells more than social sciences. But again, I used the term it feels like. I cannot conclude that there are more sales of business as compared to social sciences. Is, is there a viable difference between these two? Absolutely. Is it a real difference, or whether the difference happened just by chance? That's what a statistical software, a technique will do for me when I try to infer. At this stage, it's just a visual, but it gives you a start. It allows you to then compare between those two groups of market classifications based off of copies sold and use some kind of statistical test to check if the difference actually is real or it just happened by chance. Because the truth is, whatever we are looking at in terms of visualization is based off of the specific sample that we have chosen. And we will later on learn from our counting techniques and learning of probability that there are so many different possible samples that can be chosen from a population. What we are inferring is based off of the specific sample on which we are doing our work. And so there is only so much I can talk about while I'm visualizing. But it is extremely powerful because, as the saying goes, a picture is worth 1,000 words. It helps tell a story. And that's where charts and graphs can be extremely important. Now, if you recall the discussion we had in a previous video in types of data, the types of data oftentimes dictate the kind of chart or graph that goes with the data. And when we look into visualization in our next learning module, all of this will make much more sense. In other words, if it's qualitative data, there are only a certain set of charts or graphs that you can use. If it's quantitative data, then it's a different set of charts and graphs. If it's continuous data, there's a different kind of chart that you can use. So that's one way of looking into it, charts, graphs. Okay, so this is where you talk about bar charts, you talk about what we define as histograms. Okay, and the only difference between this guy and this guy is that there is a little bit of a gap between these bars, right? And that gap happens when you are dealing with discrete data. When you are dealing with continuous data, there is no gap. And so that kind of bar is also called a histogram. And we'll study about all of these things as we look into visualization, how to draw those, what they mean, how to define those bins, all 9 yards we'll study as part of visualization. Of course, you have all come across pie charts. We can talk about when pie charts can be used, when pie charts should not be used. How would you want to um, not just visualize the data, but report it? What aspect of data should be reported? At the end of the day, oftentimes it's not just about you students, but most people who use data, I have seen a majority of them go with the mindset that as long as I can show some colorful graphs, it comes across as if I understand the data. It's on the contrary, quite the opposite. And this is where you have to get into the shoes of the decision maker and ask yourself the fundamental question: what is it that you are after? What kind of information will help me make the decision? And this is why I again revert you back to video 1 of this learning module. Understanding the problem is critical because that will help you shape everything else that follows. What is it? What exact form of information will help me make the decision? If you are in sync with the decision maker on that part of the project, everything else falls into place. Because now you can visualize only that piece of the information and not bombard your audience with every possible visualization that you can glean from your data set, which is what most people do. It only throws people off. So what is it that you want to showcase is also equally important in terms of what you're trying to showcase. And when we talk about the visualization aspect in the learning module 2, we will also discuss certain techniques that are more powerful for certain data types as compared to others, and so on and so forth. So that's the chart and graph piece. The other part of descriptive statistics comes with numerical measures. And so by this time, you should all be extremely conversant with that summation notation. You've already done the summation preview. And that's the whole idea about how we actually build an average or a mean. You add up the numbers, you divide by the number of data values. That's essentially what is shown there. So mean is only one form of reporting. Tell yourself this. These are all reporting options. If I have 18 or 19 students in this class, if my dean comes back to me and tells me, how is this class doing? Imagine that you just wrote an exam for me. I have two options. I can narrate to the dean the scores of each one of you. That doesn't really help the dean because he is lost by the time I go to the fifth person, what the first person's score was. Or I can create an aggregate value and report that aggregate score of the class. That's where the idea of a mean comes in. It's a reporting technique that provides you a representation of all the data points in the sample. But then it comes with its own disadvantages as well. Because the mean takes all the data points equally into consideration, because here you are taking all of the data points, you are adding them up, and then you are dividing by n, which basically means that you are taking each one of those points equally important. You are weighing them equally, which is okay as long as you don't have one data point that's extremely high or extremely low. And for those of you who are nodding your head, those ones are also called outliers. So managing outliers by itself is a process. The mean is heavily dependent on outliers because in the calculation of a mean or an average, all data points are equally weighed. So as an example, in my class, if most of the class gets a score in the 60s and 70s and one person gets a 100, that person ensures that my mean is bumped up. On the other hand, if most of the class gets a score in the 70s and 80s, and one person gets a score of 10, then that person pulls my mean down. So outliers, therefore, also require you to decide whether you want to include the outlier in your judgment, in your reporting or not. If I'm reporting an overall value to the dean, and if there is only one case in my class which is very high or very low, I would rather take it away and report, because that is not the best representation of my data points. However, if I have a cluster of students who are low and a cluster of students who are high grades, the mean comes to a middle point. There is no outlier as per. All of them have to be reported. It's probably then one student group is understanding in a different way than the other student group, or one student group is more diligent, puts in more effort than the other student group. But in those cases, you cannot not report the outliers. And so when you graph the data, that graph will also show you if there are outliers. Single outlier versus multiple outliers. Is there a certain cluster of points that kind of tells a certain story? Are my males different from females in terms of grade? Are my married males different from unmarried females in terms of grade? And so on and so forth. I can look into all of those possible storylines using these charts and graphs. So mean is just one way of reporting. The other way of reporting is using a median. The median essentially takes the central value of the data set when it is arranged in an order. Order meaning either in ascending or in descending order. So that way, it doesn't really matter if there is a higher or a very lower value in the data set. The median always takes the middle section, and therefore the median is independent of outliers. It's outlier resistant. The mean is not outlier resistant. But most statistical analysis and tests are done around the mean, and therefore the mean is the most widely used metric or measure among all the other descriptive measures. Then you have certain measures of dispersion, of how the data is spread. That's where the idea of variability comes in. Okay, range, standard deviation, and so on and so forth. We'll come across something called the 5 numbers summary or the box plot. That is also a great way of understanding how the numbers behave, and especially when you are comparing two columns of data, that's a great way of comparing that data in terms of volatility and risk and so on and so forth. Okay, so all of those are part of what we define as descriptive procedures. It gives you a smell test. It gets you ready to understand what kind of statistical test you want to perform on the data set. And so once that is in place, then you look into what we define as inferential statistics. This is where you want to analyze data to decide with confidence, and based off of that analysis, you want to infer to the problem. That's where you close the loop. You had defined the problem here based off of your hypothesis, right? You set up a problem, you set up possible sets of hypotheses, you either go one direction or the other. Then you go about collecting your data. Then you go about validating the data that you have collected. Then you look into your descriptive measures, summarize the data. Eventually, you would want to infer from that data, and based off of that inference, you would relate back to one or the other form of hypothesis. You would want to see whether the stance you taken is statistically correct or not. That's essentially what you're after. So in terms of inferential procedures, there are two ways to look into it. One is estimation. Oftentimes, you really don't have population information. Okay, the entire population can be so vast that in essence, you don't know what the population mean weight is. So at the end of the day, think about it this way. And this goes back to the example that we were talking about when we were discussing hypothesis in the context of sampling. are baseball players overweight? And we said that as long as the claim is that it's 180 pounds or more, then it's overweight or it's not. Okay, so the mean weight that you are after is 180 pounds, but where do you capture that from? You don't have access to the entire population of every single person who plays baseball. You can only choose a well-educated estimated sample. And based off of that sample, you are trying to make inference about the underlying population. And so you're trying to estimate the population mean weight using the sample mean weight. And you're using sample evidence to test the claim that the population mean weight of baseball players is 180 pounds. And the claim again could be that population mean weight of baseball players is more than or equal to 180 pounds, which can also be phrased as at least 180 pounds. Depending on how you frame your claim, you frame your hypothesis based off of that. And we will discuss this exact same thing later on in this class when we decide on hypothesis testing. It's a extremely interesting proposition, but as of now, the most important takeaway for you is to ensure that you understand this overall concept of data-driven decision making. We will build on this when we meet in class on the 25th, and we will review a few examples, and we will see how we can build on this learning and apply those learnings into those examples. Till then, ciao.